any doubts that the students may have in the course Transport Phenomena. And I have with me Miss Etisri Panda, who is the TA for this course, and she and I will try to answer any queries that you may have regarding our teaching or any of the topic on any of the topics or any of the boundary conditions, the governing equations, physical meaning of the dimensionless groups, and so on. So as I understand, we already have a few questions which have been posed to us, and I would request Etisri to read each question, then I'll try to answer. And if there is any other subsequent query, follow-up query, I will try to answer that as well. So we'll follow this format throughout this session, and I would request Etisri to read out the first question. And in some situations, it will be necessary for me to discuss with Etisri, and if anyone is present in the live stream, so that I can be more clear about the inherent concepts involved with the question. So Etisri, the first question, please.
Sorry, sir. So the liquid flows on an inclined plane because of gravity, and there is no imposed pressure gradient. So the professor has already explained earlier, two conditions will prevail in this case: no velocity at solid liquid interface and no shear at liquid vapor interface. The student asks, what will be the case in liquid-liquid interface?
Okay, that's a very good and pertinent question, because so far what we have discussed in our discussion so far is a situation in which we have a liquid-solid interface, or a situation where we have a liquid-air interface or liquid-vapor interface. The conditions which we have used for the case of liquid-solid interface is no slip, where there's not going to be any relative velocity between the liquid and the solid stream. So if the solid is at rest, then the fluid layer adjacent to the solid will also be at rest at that point. And if it's a solid, if it's a liquid air situation, in that case, what we are going to have is a no shear condition, where there will be no shear across the liquid air interface. The situation will be slightly different when we have a liquid-liquid interface. When we have a liquid-liquid interface, then there would be continuity of velocity. So velocity on liquid A side of the interface must be equal to the velocity on the liquid 2 of the interface. And what I am going to do right now is I'm going to draw a figure. I'm going to share my screen and draw a figure of what would such an interface look like, and then we'll start from there. So I'm going to share my screen and show you the So Etisri, is my screen visible to you?
Yes, sir.
Okay. So what we are going to do then is, let's say, this is the interface between liquid 1 and liquid 2. And because of some reason, I have a velocity. I have, let's say, this is a part of a broader inclined plate. So this is the inclined plate along which liquid 1 and liquid 2 both are traveling one on top of the other, depending on the density of the two liquids. And there is a clearly marked interface between the two liquids. So if that's the case, and then there is some velocity profile which has developed in both in liquid 1 and liquid 2. Let's say this is also a solid plate. Now the condition would be such that the velocity, let's see if this is the velocity profile of 1, and the velocity profile of 2 could be something different. So this is the velocity profile of 2. So 1 and 2 could be substantially different, but at the interface, the velocity of liquid 1 on one side of the interface must be the velocity of the liquid 2 on the other side of the interface. So this is the condition which must be maintained for a liquid-liquid system, for a liquid-liquid interface. And not only there is going to be the continuity of velocity, there has to be continuity of shear stress as well. So the shear stress on the liquid one side of the interface must be equal to the shear stress on the liquid two side of the interface. So these two are the pertinent boundary conditions to be used for a liquid-liquid interface. So if there are no follow-up questions on whatever I have just mentioned, then I guess we can move to the next question.
So should I ask? Okay, sir. The next question is,
Itisri, I would request you also to keep a tab on
yes.
this, so that if there is a follow-up question on what I have just described.
Yes. No, sir, not yet.
All
There
right.
is no follow-up
Okay.
question now.
All right.
So let's go to the next question.
Yes, please.
Okay. So Anurag Barsani asks why the form of conductive momentum transfer is force, as by units we get force unit, but actually it's a momentum transfer.
Okay, that's a good question. I suppose you are talking about the Navier-Stokes equation, in which case we have the convective momentum on the left-hand side of the equation and conductive momentum or the viscous transport of momentum on the right-hand side of the equation. And the right-hand side of the equation also contains the pressure gradient as well as the body force. Pressure gradient is expressed by dpdx term. The body force is expressed by rho gx term, and the diffusive momentum is expressed by mu times del square vx by del x square, del square vx by del x del y square, and so on. These are the terms. So I'm writing these equations from memory, and there could be some difference in what I am, and Itisri can tell me if there's anything that's wrong. It is del Vx del T would be the first term, which is the transient term in the Navier-Stokes equation, plus Vx del X, and other terms like Vy del Vx del Y, and so the term. On the right hand side, I have minus del P del X term plus mu times del square Vx del X square plus del square Vx del Y square, and a Z term. And then we have this plus rho Gx term, where Gx is the acceleration due to gravity, or the component of that of the body force in the direction of gravity. So the question of the student is related to, probably, as if I understand correctly, is on this term. So this term essentially tells us about the momentum transfer by convection. So your question is why the unit of this, why this is in force, whereas we are talking about momentum. Is this right? That was the question, isn't it?
Yes, sir.
Okay, so if you look carefully, you would see it's not just momentum, it's not just the change of x momentum, it is the time rate of change of x momentum. So if you work out each of these terms, you would see that essentially you're talking about the rate of change of momentum, and the rate of change of momentum is nothing but force. So that's why all terms in Navier-Stokes equation are force per unit volume. So let's talk about this term, where pressure is force per unit area, and you have another length scale over here. So this is another 1 by L. So this is nothing but force per unit volume. The same applies to each of the terms on the left hand side. So on both sides. So what you see essentially is convective momentum transport, but it's not just convective momentum transport, it is a rate of convective momentum transport. That's why it's force per unit volume in all these cases. Ithisri, is if there's any follow-up question, you are
Okay.
going to remind me. And
Right.
so far, I have answered two questions. One on the interface between two. What are the boundary conditions on the interface between two liquids? And the second question is about the significance of the term in Navier-Stokes equation.
Yes.
And I get, is there any follow-up question on these two
No,
in the
sir,
four?
not yet. No.
All right.
I'll let you know if there is. So let's go to
Okay.
the third
Third
question.
question.
Okay.
Yes,
So
please.
why dimensionless analogies are so important in TP, HT, and MT?
What are the three things that you said in?
Transport phenomena, heat transfer, and mass transfer. Why dimensionless analogies are so important?
Okay. So the let's talk about the dimensionless groups which are relevant in, let's say, momentum transport and in heat transfer and in mass transfer. So in momentum transfer, what you see, the important one for this case, the dimensionless group is Reynolds number. In heat transfer, I mean the convective heat transfer process. I'm not discussing about the free convection heat transfer at this moment. They are going to be Reynolds number and Prandtl number. Okay. And in mass transfer, it's surely going to be Reynolds number, but in addition, in place of Prandtl number, it's going to be the Schmidt number. And the factor and the other one, the major dimensionless group, which contains the engineering parameter. And by engineering parameter, I mean the parameter of interest in any engineering calculation, which for heat transfer, you know that this is the convective heat transfer coefficient. And for mass transfer, this is the convective mass transfer coefficient. And for the case of momentum transfer, this has to be the friction coefficient CF that we know, which would tell us something about the importance of friction when a liquid and a solid, when a fluid and a solid are in contact. So the corresponding dimensionless number here is Nusselt number, and here this is going to be Sherwood number, and this is some sort of a friction coefficient F. So the entire study of transport processes in chemical engineering deals with evaluating the correct value of F, the friction coefficient, Nusselt number, or in other words, the heat transfer coefficient, Sherwood number, or in the case of mass transfer coefficient. Now it may so, and the presence of the Reynolds number in momentum transfer as well as in heat and mass transfer make the heat and mass transport process coupled with the momentum transport process. So you need to find out what is the velocity distribution, what is the velocity distribution in momentum transfer by solving the Navier-Stokes equation. Only then you would be able to solve the energy equation to find out what is the temperature distribution, or you can solve the species equation to obtain what is the expression for the concentration of one component A variation in mass transfer. So there is a one-way coupling between these three. In order to solve for either temperature or concentration, you need to know the velocity expression. In some of the examples that I have shown in the case of transport phenomena, you have seen that it's extremely difficult to obtain, even for the case of momentum transfer, what is the expression for the friction factor F. That means to solve for the velocity expression, to obtain the velocity expression, and from the velocity expression, obtain the expression for the friction coefficient. So you could well imagine that when there is a coupling between the momentum and the heat transfer, it is difficult to obtain the temperature profile and the same applies for the concentration profile cases. On the other hand, from a practical point of view, for some cases, it may be possible to do a large number of mass transfer experiments and obtain a correlation or a relation for concentration variation. But due to some reason, it is not possible for the case to conduct heat transfer experiments. Or the other way around. Let's say you can measure the temperature easily, but you cannot measure the concentration that easily in a system. So while performing the heat transfer analysis, you measure the temperature under different conditions and come up with a relation that connects the Nusselt number with Prandtl number and Reynolds number. But the same experiment, if you like to find out what is the Sherwood number situation, the mass transfer experiments cannot be performed because you're dealing with a toxic material, or if you have mass transfer data, but you cannot do the heat transfer experiments, let's say for the case of a very heat sensitive material. So as an engineer, you'd like to extend your knowledge of mass transfer into heat transfer, or your knowledge of momentum transfer into heat transfer. So in ideal world, you would be able to solve for V, T, and Ca and obtain an expression for friction factor, Nusselt number, and Sherwood number. But in most of the realistic situations, you'd be happy to obtain one of these relations, let's say the Nusselt number relation, through experiments, but you cannot perform the mass transfer experiments or the momentum transfer experiments. So is there a way by which your knowledge of one transport process can be extended, can be extrapolated to another transport process, be it momentum or be it mass? And here comes the beauty of analogy. So if you have followed my lectures, you would see the first step in analogy is to write the governing equation in equations for momentum transfer, for heat transfer, and for mass transfer in dimensionless form. And when you write them in dimensionless form, these similarity parameters, which are Reynolds number for the case of case of momentum transfer, Reynolds and Prandtl for the case of heat, and Reynolds and Prandtl for the case of Schmidt number, they will appear automatically in that equation. And for the simplest possible analogy, which is Reynolds analogy, there you would see that the governing equations and the boundary conditions will become identical when Prandtl number and Schmidt number both are equal to 1. That is the most restrictive form of analogy, which is known as the Reynolds analogy, where Prandtl and Schmidt number equal to 1. And the analogy simply tells you that if history, you probably should tell me whether I'm doing it correctly or not, that F or F by 2 is equal to Sherwood number, the average Sherwood number is equal to Nusselt number, or the correct form I think is going to be F, then this is Stanton number equals Stanton number based on mass. So what is Stanton number? Stanton number is defined as Nusselt by Reynolds times Prandtl number. Okay, this is Stanton number based for the case of heat, and for the case of Stanton number based on mass, this Prandtl number would be replaced by the Schmidt number. So for the case of Reynolds analogy, the Prandtl and Schmidt number are taken to be equal to 1. That's a very restrictive condition. And what you get is the Nusselt number is equal to Sherwood number. Now, obviously in realistic situations, you are not going to get a fluid whose Prandtl number and Schmidt number are equal to 1. So the extended form of the analogy, Reynolds analogy, is known as the Chiltern-Colburn analogy, where a correction factor for Prandtl number and for Schmidt number are added in here. Okay, so this corrected form of the Reynolds analogy, which is known as Chiltern-Colburn analogy, essentially gives you the equivalence between heat transfer and mass transfer. So through some experiments, if you know the Sherwood number relation, then you should be able to obtain the Nusselt number relation as well. That is the beauty of the analogy process. I do not recall what exactly is the correction factor going to be. So Ithistri, you can probably help me
Yes.
in that. What is the
It's
exact form of
Sir, it is 2 by 3.
2 by
10 to the
3?
power 2 by 3, yes.
Can you dictate what this is going to be?
F equal to Stanton
F
to the power
equal to Stanton to the power
2 by 3.
2 by 3.
Yes.
And so it is going to be Stanton based on mass to the power 2 by 3, right?
Yes. Yes.
Okay, so whatever it is, you can see it in your text, and this essentially tells you this or some variation of this will tell you the utility of the utility of the similarity analysis, the analogy where knowledge of one type of hit, one type of process, or knowing an expression for one type of the process can be used to obtain what is the expression for the other type of process. And to a practicing engineer, the importance of this cannot be overemphasized. So you cannot do an heat transfer experiment for a specific geometry or for a specific chemical or for a specific chemical coated surface, but you can do mass transfer experiments. So you do mass transfer experiment, get what is the expression for Stanton number going to be, and then use the analogy to find out what is going to be the Stanton number based on heat, or what's the expression for the Nusselt number for such a case, or what's going to be the friction factor for such a case. So for designing an experimental setup or for a new geometry, for a new material, this kind of analogy is of real importance, real utility for any practicing chemical engineer. I hope this has answered your query, and I'd be happy if you have any uh, follow-up question on this. Ithistri, is there anything else right now?
No, sir. That is all. There is no follow-up questions.
Okay, so we'll wait for some more time because there
Okay.
may be other people are watching this and they may have other questions which they are going to pose live to us, and we'll try to answer them.
Okay.
So we'll wait for inputs from the students' side.
Okay. Sir, there is another question.
Okay, good.
Is there any case where the slip condition, that is fluid velocity at interface, is not same as surface?
Okay, very good question. So I would go back to this, and the question over here, what I understand is that I have a surface, no, and let's say a fluid is flowing over it, and this is the y direction, and over here is the x direction. And the y starts from this is the starting point of this. So the no slip condition with which we are mostly dealing with in the course is that Vx at y equals 0 is equal to 0. That is what the no slip condition is all about, that there is no relative velocity between the fluid and the solid. Whatever be the velocity of the solid plate at the interface, that's going to be the velocity of the liquid as well. But as the question has been posed about the validity of no slip condition, or the situation in which no slip condition is going to be disobeyed, the we are dealing with continuum mechanics in this case, and the continuum mechanics tells us that we are going to have uniform property of the fluid in this specific case, and it's not a rarefied fluid. If it's not a rarefied fluid, let's say if it's not a rarefied gas, then the no slip condition would always be going to be valid. But if it's a case in which the molecules are widely apart from each other, as would be the case for a dilute gas under very small pressure, then what would happen is that the mean free path of the molecules is going to be comparable in size with the system dimensions. So if that's the case, then the molecule of the liquid may not be stuck to the solid at the interface. This is a very largely enlarged view of this very large view of the molecule, but it's rather going to come, strike the surface, and can bounce off. So there's in going to be incomplete momentum transfer at the interface, and therefore the molecules will have a value, will have some velocity at the liquid solid, at the fluid solid interface as well. See, in those situations, it is customary to use a slip condition with the Navier-Stokes equation. So if we think about if we are going to divide the situation that we have for the case of uh, for this case, let me show you this, which is not exactly what we have covered in our course, since it's with the continuum. We are dealing with continuum. So first you are going to have continuum where Navier-Stokes equation is valid. Okay, and then you have the slip flow regime where, as I mentioned, that the same continuum equation, for example, the Navier-Stokes equation, can still be used, but with a slip flow condition. Okay, so the slip flow condition simply provides a finite velocity of the fluid molecules bouncing off the surface of the solid. However, it is still the continuum models, for example, Navier-Stokes equation can still be used provided we use a slip flow case. And on the top, we have the free molecular flow where the continuum limit is totally breached, and this can be modeled only by molecular theory, the kinetic theory. Okay, so there's no question of no slip condition in here. Molecules freely strike a surface, bounce back to the bulk, and they will strike a surface and travel well over travel a large distance before they encounter another molecule of the fluid. And of course, the kinetic theory is the model which is to be used here. So from Navier-Stokes equation on one side and molecular theory on the other side, we have several variations in between as well, where the molecular dynamic simulation is used to predict the behavior of a system. But for the present course of transport phenomena, we have restricted ourselves to this continuum flow cases where the no slip condition is always valid. The engineering applications that we are mostly concerned with, we can definitely assume continuum cases. We can use Navier-Stokes equation. We can use no slip. But as the system size decreases with the advent of microfluidics and small microchannels through which flow are taking place, and surfaces, different types of surfaces are getting involved, becoming important from an engineering sense, the slip flow model has been recently finding increased use in those cases where we are dealing with microscale transport processes, microscale flow of liquids through the channel. So for those cases, slip flow model is to be used. But for the present course, we are using a completely continuum approach in which the Navier-Stokes equation is valid. If there's any other question. So these are
No, sir.
all, I'm sorry, I forgot to mention, these are all in the increasing values of Knudsen number. So Knudsen number tells us something about how close to what is the system's dependence on system size, the characteristic dimension, and the mean free path. So a very small value of Knudsen number essentially tells you that continuum models can be used, whereas gradually increasing values of Knudsen number will tell us that we are going away from continuum and going towards a free molecular flow regime, where kinetic theory is the only theory which should be used to predict anything in the flow situation. But in our course, it's only continuum. So I guess we are halfway through, or more than halfway through the session. And as my previous experiences go, we'll wait for some more time to see if there are any queries or any responses.
Okay, sir. So there is another question.
Okay.
Can you please elaborate on modeling the velocity distribution in an polymer extruder with screw flights to increase the shear rate, I guess? How can we treat such melt polymer flow at high temperatures?
Can you repeat the question once again? It's not very clear
Okay.
to me.
Can you please elaborate on modeling the velocity distribution in an polymer extruder with screw flights to increase the shear rate? How can we treat such melt polymer flow at high temperatures?
Okay. I Since the specifics are not provided about the nature, about the system geometry, design, and so on, and the nature of the polymer in terms of its property and the temperature dependence of that property, I would rather give a general explanation of how to proceed in such a case. There are two things which are quite common in this is that we are trying to increase the shear rate on the polymer fluid, and at the same time I'm exposing it to a high temperature, most likely to change the flow index, the flowability of the fluid of the polymer. So the equation that is to be used for shear stress, it's definitely not going to be a Newtonian fluid. It is a non-Newtonian fluid for which the shear stress strain relationship must be evaluated a priori before you start solving the equation. So your governing equation will still be the Navier-Stokes equation, but it's going to be the Navier-Stokes equation where you can where which is going to be equation of motion and not equation of or not Navier-Stokes equation. So if you look at, for example, the Bird-Stewart-Lightfoot, there are two different types of two different ways by which Navier-Stokes equation are presented. One is where the del x of tau xy, tau xz, etc. are kept in the equation. And in the second case, for the Navier-Stokes equation, in which the mu and rho are taken to be constant for a Newtonian fluid, we get the relation where the viscous term is going to be mu times del square Vx by del x square plus del square Vx by del y square, and so on. So your problem fits, as I understand, fits at the equation of motion level and not Navier-Stokes equation, not in the Navier-Stokes equation. You would rather start with the more general form of the equation where the expressions are going to be in the form of shear stress and not in the form of velocity gradients. So when you have the shear stress, there you are going to supply with the dependence of the shear stress on velocity gradient, which is unique to the polymer under that level of shear which you are forcing it to pass through. That's one point. So from a uh, from a fluid mechanics point of view, you need to know what is going to be the shear stress expression and use that in the equation of motion and not in Navier-Stokes equation. Secondly, you're also going to talk about the high temperature. You have mentioned about high temperature. And when you mentioned about high temperature, if let's say the polymer that you are dealing with has a low thermal conductivity, which many of the polymer materials have, then there's going to be a temperature difference at different points of the polymer fluid. So if you have a different 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 velocity, different temperature at different points in the polymer, then what you can expect is that the viscosity will also vary at those points. So you need to solve the equation of motion and equation of energy simultaneously, because right now there's a two-way coupling between fluid mechanics and heat transfer, momentum transfer and energy transfer. Your energy transfer dictates what's going to be the temperature at every point and what is the viscosity at every point for that material. Secondly, the fluid mechanics part tells you what is going to be what is going to be the temperature difference at every point in the flow field. So velocity field will dictate temperature field. Temperature field will tell you the viscosity variation. Viscosity variation is going to change the flow field. So this kind of coupling requires that the solution is to be simultaneous. The heat transfer and the fluid mechanics part will have to be solved simultaneously together, I mean. So two things are prerequisite. One is what is the stress that you are going to apply in the extruder, and what would be the stress strain relationship to be used for that polymer in equation of motion. And second is how does the viscosity of the polymer melt vary with temperature. So therefore you need to solve the energy equation simultaneously as well. Once you do that, then you have the true picture of what is happening in a polymer extruder at high temperature. Idisri, any other question?
Yes, sir. Another one.
Okay.
This is another request to please once explain the equation of change that includes total time derivative and substantial time derivative.
Once again, repeat the question so as to.
Okay. Please once explain the equation of change that includes total time derivative and substantial time derivative.
Okay. I guess this question is deals more with the concept involved in total time derivative, substantial time derivative, and partial time derivative. And if you look at the vector expression of, let's say, the Navier-Stokes equation in your textbook, which is Bard Stewart Lightfoot, you would see the capital D dt, where both D's are in capital, that are used for substantial derivatives. And you can write the normal derivative out of the substantial derivative as well. And my lecture has given you the details about the substantial derivative and how what is the definition of substantial derivative in relation to partial time derivatives. So partial time derivatives is a derivative in which the xyz, the origin of the coordinate system, is fixed and you are measuring something as a function of time. So if you stand at a point and you measure something going past you, what you are measuring, the time variation of those things going in front of you is the partial time derivative. So if you are standing somewhere and you are measuring those you are measuring or you're counting how many of the students going in front of you are wearing spectacles. So if you are standing still, then the variation of the number of students wearing spectacles passing you is the normal derivative, is the partial time derivative. So del C by del T, where C is the number of students having spectacles. There may be situations in which you have a velocity of your own, your velocity, fixed velocity. You're moving in a car and you are still measuring the number of students passing you who are wearing spectacles. So this number is now going to be influenced by your velocity, your which direction you are going, how fast you are moving, and so on. So when the coordinate system has a velocity of its own, that's the total derivative. And let's say that all these you are standing in with a bunch of students who are going in a random fashion. When a class begins and a class ends, there will be a lot of exchange, a lot of movement of students from one class to the other. So they will have some average velocity at any given instant of time and space. So if you let yourself move, let yourself float with the students at any given location and time, but you are still measuring the number of students passing you who are wearing spectacles, that is the substantial derivative. and that is what is expressed in my class notes and in your textbook as ddt, capital ddt. So it has a time variation part and the velocity, average velocity of the students. The component of velocity is vx, vy, and vz at that time. So if C is the number of the students who are wearing spectacles, then let me show you. If C is the number of students who are wearing spectacles, then the substantial derivative, the definition of the substantial derivative, uh, and Ithistri, you tell me if I am missing certain terms.
Okay, sir.
So this is what the definition of substantial derivative, where Vx, Vy, and Vz are the components of the velocity of the fluid, components of the velocity of the students who are milling around you in, in there. So the number of students wearing spectacles that are passing you when you are moving with the general flow of students having velocities Vx, Vy, and Vz is known as the substantial derivative. So now if you look at the Navier-Stokes equation, which obviously I cannot recall right now, all these ddt's are the substantial derivatives, and when you expand them you get all these four terms for the Cartesian coordinate system. But conceptually, one, if you are static, then this is what you are going to measure. If you are moving with the velocity of the fluid, these are the additional terms which are to be added to give you a correct estimate of the number of students wearing spectacles passing you when you are moving with the fluid. If you have a specific velocity of your own, then these things are going to change as well. So that's essentially the concept of substantial derivative and partial time derivative, and how they're used in Navier-Stokes equation, or in terms of temperature. So if it is temperature, then C is going to be replaced by temperature, and it's going to be del temperature by del time, Vx del temperature by del x, delta Vy del temperature by del y, and so on. So that's the inherent concept involved in this.
There is no more question currently, sir.
Okay, let's wait for 5 more minutes.
Okay. So there is another question, sir. Sir, can you hear me?
Yes, please tell me.
Okay. If fluid is turbulent and moving between two plates have relative motion with each other, then how can we drive the velocity and momentum equation?
One more time.
If fluid is turbulent and moving between two plates, the two plates I think have the relative motion with each other, then how can we drive the velocity and momentum equation?
I think I am paraphrasing the question. What I understand is the student wants to know if we have turbulent flow and in between two plates where there is relative motion of the two plates, then how the equation can be derived, how the velocity expression can be derived. So I think he or she meant derive the equations. Is that your understanding, history?
Yes, yes.
Okay. So what I believe the question is, the question is about a common situation which is Queth flow, and in the Queth flow what we have seen previously is that we have a solid plate and another solid plate, and we have a liquid in between. One of the plate is moving, let's say, with some velocity of its own, and the other is stationary. And there is no pressure gradient present in this. So if there is no pressure gradient present in this, the use of Navier-Stokes equation would simply provide with a velocity profile which would be linear. In absence of any pressure gradient, it's going to be linear, where due to no slip condition at this point, the velocity is going to be equal to v, and due to no slip condition, the velocity at the other end is going to be equal to 0. So this is what the profile is going to look like for the case of laminar flow. And when you are using Navier-Stokes equation to solve for the profile, this is the profile you are going to get. But the question that is asked is more, it's what I understand is it's different, is that I have the same two plates, but I have a situation in which the flow is no longer laminar, but it's going to be turbulent. So first of all, if it is turbulent flow, I cannot use Navier-Stokes equation in the form which we have seen so far. So our form of Navier-Stokes equation uses the case that the flow is laminar and there is no intermixing between the two. And if it is a turbulent flow, then besides the stresses which are present in laminar flow, additional stresses which are known as Reynolds stresses, they would also have to be taken into account, which makes the profile for flow, the Navier-Stokes equation for such a situation is going to be extremely, how would I put it, cumbersome to use. If I can quickly show you what it would look like, uh, I was just this is what it would look like for the case of turbulent flow. So you are going to have fluctuating velocity components, and the velocity is going to be the time smooth velocity, which is the red color, and the fluctuating, so instantaneous velocity is going to be equal to the time smooth velocity and the fluctuating velocity. So this is what it's going to look like. And when you put that concept, that velocity, instantaneous velocity, is the sum of vz. The instantaneous velocity is the sum of the time smooth velocity and the fluctuating velocity. When you put this expression into Navier-Stokes equation and take the time average of that, the red colored terms, additional terms, are going to appear. They are going to be Reynolds stresses. So it is almost impossible to use the way in the treatment method that we have done for the laminar flow situation, in which case the equation was pretty straightforward, and we were able to obtain the laminar profile for the velocity. So in order to take care of the complexity associated with the fluctuation in turbulent flow, which essentially means additional momentum transfer, there's something called an universal velocity profile due to the scientist Prandtl, where he divided the velocity into three layers: a viscous sublayer, which is very close to the solid interface, where the viscous forces are going to be important; a turbulent core right at the middle, where viscous forces are absent; and the transition region in between, where both are going to be present. So this also is not very easy to use. So there is a third method, which is known as the power law method, where the velocity is expressed in terms of a y by r to the power 1/7, since it's and which is purely empirical in nature. So this 1/7 power law has been widely used for for expressing the velocity profile for turbulent flow. So this and the subsequent derivation, which I think I have shown you in the transport phenomena course, where the wall shear stress can be obtained, and other calculations can be made. So it is not possible to obtain a velocity profile like what you see in here, but I can tell you something about the qualitatively how would it behave. So let's say that we have a situation in which I have laminar flow, and in another case where I have turbulent flow. What would happen in the case of
Uh,
flow?
Hello,
Yes,
sir.
please. Yes, please.
Sir, actually, already we have passed the time out, sir.
Okay, so I'll,
Actually, we
I'll
have
quickly.
more live session.
I just 30 seconds.
Okay, okay, sure, sure, sure.
In a laminar flow, this is going to be parabolic. In turbulent flow, the same is going to be like this. More the turbulence, this region is going to get extended. And if you go to the completely plug flow, what you are going to get is a profile like this. But these are experimentally observed, and Navier-Stokes equation, the way I have taught you, cannot be used to obtain the situation, the velocity profile of the flow between two plates when one of them is motion. So this is not possible, but fundamentally this is what it would look like. Okay, so I am done, and I understand that we have reached to the end of this live session. So I will stop here. Thank you for your participation, and thank you, Ithisri, for your help. And I would request the students to save the questions for the next live session, which we are going to have in about a month's time. So if you send your questions in advance, it would be easy for me to time my responses such that all such queries can be addressed. Thank you very much.
Thank you, sir. Thank you.
IIT Kharagpur, I am done. Can we leave now?
Yes, sir. Yes, sir.
Okay. Thank you.
Thank you.
Thank you, Itis.